Imagine a star billions of light years away that suddenly disappears, then comes back. Not once, but repeatedly. Its light fades without warning, sometimes for hours, sometimes for days, in ways that defy every rule astronomers have spent centuries decoding. Something massive is passing in front of it, yet no known cosmic object could behave like this, and the universe offers no explanation. The universe is mostly predictable, not simple but predictable. Stars are born, they burn, and they die according to patterns humanity has spent centuries studying. Their light flickers slightly, their brightness shifts gently, but always within limits. Astronomers trust those limits. Entire careers, instruments, and theories are built on them. And then this one star quietly broke every rule. In 2015, while analyzing data from NASA's Kepler Space Telescope, scientists noticed something strange. At first, it did not look dramatic. There was no explosion, no cosmic violence, just a faint dip in brightness. The kind of anomaly that usually turns out to be a software glitch, a calibration error, or dust drifting between the telescope and a distant sun. Normally, such signals are discarded, but this one refused to disappear. The star dimmed again, then again, and again, each dip deeper than the last, not smoothly, not predictably. The brightness dropped sharply, recovered partially, then fell again without warning. It looked less like a natural process and more like something was passing in front of it, something massive. This immediately posed a problem. When planets pass in front of stars, the dimming is small, often less than 1%. Even gas giants barely leave a mark. But this star did not follow those rules. The dips were huge, irregular, and violent in their timing. At its deepest point, more than 20% of the star's light vanished. That number alone made no sense. Astronomers rechecked the data, then checked the instruments, then checked the telescope itself. Nothing was wrong. The signal was real. The star was truly dimming, and no known stellar behavior could explain it. What made the situation worse was the pattern. If a planet caused the dimming, the signal would repeat at regular intervals. Orbital mechanics demand it. Gravity enforces schedules, but this star refused to obey. The dips arrived early, then late, then sometimes not at all. Some lasted hours, others lasted days. There was no rhythm, no cycle, no clean explanation. It was as if something enormous was moving in front of the star, but not in a stable orbit. As if whatever was blocking the light was changing shape, breaking apart, or assembling itself again. That idea alone was deeply unsettling. Stars exist on cosmic timescales. They do not behave erratically, they do not flicker violently, they certainly do not lose massive amounts of light for no apparent reason, yet this one did. At first, the anomaly stayed buried inside research papers and technical discussions. Only a small group of astronomers knew what they were seeing, but even among them unease spread quickly. Because the more they studied the data, the less comfortable they became. This was not a single event, it was ongoing. The star kept dimming, and brightening, and dimming again. No explosions followed, no supernova, no stellar collapse. The star continued shining as if nothing was wrong except for the fact that something clearly was. That was the most disturbing part. If the star had died, the mystery would have ended. If it had flared, the cause might have been obvious, but instead it lingered, quiet, persistent, defiant. A normal star behaving abnormally is one thing. A star that refuses explanation is something else entirely. And slowly, reluctantly, a question began to form in the minds of the scientists studying it. Not because they wanted it to be true, but because every other explanation was starting to fail. What could possibly block that much starlight without destroying the star itself? And why did it look less like a natural shadow and more like something deliberate? This was the moment when curiosity turned into discomfort, and discomfort turned into something closer to fear, because whatever was happening around that star was not something humanity had prepared for. And this was only the beginning. Why this should be impossible? To understand why this star caused so much concern, you have to understand how stable stars really are. From Earth, stars look like distant points of light, but to astronomers they are systems governed by precise physical laws. Gravity pulls inward, nuclear fusion pushes outward. For millions or even billions of years, these forces remain in balance. That balance creates consistency, predictability, trust. Stars do not behave randomly. When astronomers observe changes in brightness, there is almost always a clear cause. A planet passes in front of the star, briefly blocking a tiny fraction of light. The result is a shallow dip that repeats with clockwork precision. The timing tells scientists the planet's orbit. The depth tells them its size. This method has discovered thousands of worlds. It works because the universe follows rules. That is why the data from this star felt wrong almost immediately. The dimming events were not shallow. They were deep, not 1%, not 2%. Some of the drops erased more light than any known planet could block. To achieve that kind of dimming, an object would have to be absurdly large, larger than Jupiter, larger than anything that could reasonably exist without becoming a star itself. That alone was a red flag. But the real problem was not just size, it was behavior. Planets move in stable orbits. They repeat. If a planet blocks a star's light today, it will block it again tomorrow, next week, or next year, depending on its orbit. Gravity demands regularity. Even chaotic systems have patterns. This star showed none. The dips came early, then late, then vanished for long stretches of time. Some lasted only hours, others stretched across days. There was no repeating interval. No mathematical model could lock onto the timing. Astronomers tried, again and again. Every attempt failed. That should not happen. If dust were responsible, it should disperse. If debris were involved, it should settle into predictable paths. If the star itself were unstable, it should show signs of violent activity. It did not. Spectral analysis showed a normal, healthy star. No flares, no eruptions, no warning signs. Everything about the star said normal. Everything about its light said impossible. As the analysis deepened, the list of explanations grew shorter. Instrument error was ruled out early. The Kepler telescope had observed thousands of stars with extreme precision. Only this one behaved like this. Software glitches were checked and dismissed. Other telescopes confirmed the dimming independently. The signal was real. That realization changed the tone of the investigation. This was no longer a curiosity, it was a contradiction. Astronomy is built on consistency. When something violates that consistency, it threatens more than one theory. It threatens confidence. If a star could behave this way, what else had astronomers misunderstood? Quietly, unease spread through the research community. Papers began to circulate. Conferences included whispered discussions. Emails were exchanged late at night. The same conclusion kept surfacing, even when no one wanted to say it openly. No known natural process fully explained what was happening. That does not mean scientists jumped to extreme conclusions. Quite the opposite. Extraordinary claims require extraordinary evidence. Every mundane explanation was pushed to its breaking point. Comet swarms, dust clouds, collisions, stellar oscillations, each explained part of the data but never all of it. There was always something left over, some detail that refused to fit. That leftover detail mattered. Because in science, anomalies are not ignored, they are pressure points, places where understanding cracks, and when enough pressure builds, something new emerges. At this stage, the mystery star had done something rare. It had forced experts to admit uncertainty, not temporary confusion, fundamental uncertainty. They did not know what they were looking at. And when the universe presents a phenomenon that does not match any known category, the question is no longer what is happening. The question becomes far more unsettling. What kind of thing could exist that behaves like this? That question lingered unanswered as the data continued to arrive. And then someone noticed a number that made the situation far more disturbing. The number that changed everything. For a while, the mystery of the star lived in patterns and behavior. The timing made no sense. The irregularity raised alarms, but it was still possible, at least in theory, that some rare natural process was responsible. Strange did not yet mean impossible. Then someone calculated a single number. And everything changed. Astronomers measure stars by their brightness with extreme precision. Even tiny fluctuations are meaningful. Most exoplanets discovered by Kepler cause a dip of less than 1%. That is enough to confirm their existence. A gas giant might block 1 or 2% if conditions are perfect. Anything beyond that is unusual. This star did not follow those expectations. When researchers isolated the deepest dip in brightness, the result was startling. The star lost more than 20% of its light, not momentarily, not as a brief flicker. but sustained long enough to rule out noise or error. 20% is not a rounding error. It is not a subtle fluctuation. It is catastrophic by astronomical standards. To put that into perspective, imagine something blocking more than 1/5 of the sun's surface as seen from Earth. No planet could do that. Even Jupiter would barely register. To block that much light, an object would need to be enormous, vast beyond anything found in typical planetary systems. This was the moment when skepticism hardened into concern. Scientists rechecked the measurement, then recalculated it independently. Different teams using different methods arrived at the same result. The number held. The star really was dimming by that much. This forced astronomers into a corner. Size matters in space. Objects of that scale cannot exist casually. They collapse under their own gravity. They heat up, they glow, they leave signatures. Yet here was something blocking light without revealing itself in any other way. No heat signature appeared. No gravitational disturbances were detected. No companion star was visible. Just darkness passing in front of light. Worse still, the 20% dimming was not an isolated event. Multiple dips approached similar depths. Some were smaller, some were nearly as extreme. Together, they painted a picture of something large and uneven moving across the star's face in fragments or clusters. That detail was deeply troubling. A single large object might be explained with enough imagination, but a complex, irregular structure implied either chaos or design. Natural systems tend toward symmetry. They form disks, rings, clouds, predictable shapes. This did not resemble any of them. At this point, the conversation shifted. The question was no longer whether the star was strange. That was beyond dispute. The question became what kind of structure could cause this effect without announcing its presence in any other way. This is where a speculative idea resurfaced. One that had existed for decades, largely confined to theoretical discussions and science fiction. An idea that most scientists preferred not to touch because of how easily it could be misunderstood. A structure built around a star. Not a small one, not a station or a ship, but something vast, something capable of capturing energy on a stellar scale. A megastructure so large that it could block enormous portions of light while remaining cold and dark at a distance. The idea was uncomfortable not because it was impossible, but because it was plausible in a way that felt dangerous. No one claimed it was the answer, no one wanted it to be, but when the data was laid beside the theory, certain pieces aligned more neatly than expected. Irregular shapes, massive coverage, no obvious heat, no natural symmetry. It was enough to make people uneasy. Scientists did what scientists always do in moments like this. They tried to kill the idea. They searched for flaws. They demanded alternative explanations. But the 20% number refused to go away. It sat there immovable, demanding an explanation proportional to its scale. That number transformed the mystery from curious to unsettling. Because the universe is vast, but it is not careless. Things that block that much light are not supposed to exist quietly. And yet, something out there was doing exactly that. Whatever the explanation would eventually be, the implications were already clear. This was not a small anomaly. This was not a minor oversight. This was a phenomenon large enough to challenge assumptions. And soon, the discussion would cross a line that scientists rarely cross publicly. Not because it was exciting, but because the data left them no other choice. A pattern that should not exist. In science, patterns are everything. Patterns are how astronomers predict eclipses centuries in advance. They are how planets are discovered without ever being seen directly. They are how chaos is separated from meaning. When a pattern exists, it points toward a cause. When it does not, something fundamental is wrong. The star in question refused to cooperate. At first glance, the dimming events looked random, but randomness in astronomy is rare. Even complex systems eventually reveal structure. Astronomers believed that if they observed long enough, a rhythm would emerge, an orbit, a cycle, a repeating sequence that could anchor an explanation. It never happened. The dips came too early, then too late. Sometimes they clustered together, sometimes months passed with nothing at all. There was no dominant period, no repeating interval, no orbital solution that worked. This was deeply unsettling. If a planet were responsible, its motion would be dictated by gravity. Gravity does not improvise, it does not skip schedules. Even comets with their elongated orbits return on predictable paths, debris disks settle into symmetry, dust clouds spread and fade. This star did none of those things. The timing of the dimming events changed from year to year. Some dips were sharp and deep, others were shallow and prolonged. The shapes of the light curves varied wildly. It was as if the object blocking the star was changing shape, breaking apart, or rearranging itself over time. That implication carried weight. Something that large, behaving that erratically, should not remain invisible. It should heat up, it should collide, it should stabilize or destroy itself. Instead, it persisted. Astronomers tried modeling everything they could think of. Massive swarms of comets passing in front of the star, clouds of dust left behind by catastrophic collisions, even chains of disintegrating planets. Each model could reproduce part of the data, but only by stretching assumptions to uncomfortable extremes. The comet hypothesis required hundreds of enormous comets arriving at precisely the right angles. The dust models demanded particle sizes and distributions never observed elsewhere. The collision scenarios raised questions about where the debris went and why it did not glow. Every explanation solved one problem and created two more. What made matters worse was that the dimming events were not uniform. Some blocked light abruptly as if a solid edge had crossed the star. Others faded in gradually as if something diffuse was involved. The combination suggested a mix of structures rather than a single object. That mixture was difficult to reconcile with natural processes. Natural systems tend toward simplicity. Complexity exists, but it usually emerges from simple rules. What astronomers were seeing here felt layered, fragmented, almost engineered in its inconsistency. That word was never used lightly. Most researchers avoided speculative language in their papers. The official tone remained cautious. But privately, discussions grew more intense. Emails circulated with phrases like difficult to explain and inconsistent with known models. At conferences, this star became a topic of quiet fascination. The data was not screaming an answer. It was whispering a warning. One of the most troubling aspects was longevity. The dimming persisted across years of observation. This was not a brief event or a transient phenomenon. Whatever was causing it was stable enough to remain in the system for extended periods, yet unstable enough to defy prediction. That combination should not exist. If the structure were stable, it should be predictable. If it were unstable, it should not last. Yet here it was, doing both at once. The deeper astronomers looked, the more the mystery resisted simplification. Every attempt to impose order failed. The pattern was not hidden, it was absent. This forced an uncomfortable realization. The assumption that the system must behave like others might be wrong. This might not be a familiar category at all. It might represent a class of phenomena humanity had never observed before. And that realization opened the door to ideas that had been previously dismissed as too extreme. Because if no natural pattern existed, then perhaps the structure causing the dimming was not natural in the way scientists expected. Perhaps it was not a single object. Perhaps it was not accidental. Perhaps it was not governed by the same constraints as planets or dust. That possibility hovered in the background, unspoken but increasingly difficult to ignore. And soon, someone would articulate it openly. Not as a claim, not as a conclusion, but as a question that could no longer be avoided. The theory scientists did not want to say out loud. There are ideas in science that exist quietly in the background. They are mathematically sound, they are physically possible, but they are rarely discussed in public, not because they are wrong, but because of what they imply. This was one of those ideas. For decades, theorists had speculated about advanced civilizations and how they might solve the problem of energy. A civilization that survives long enough inevitably faces limits. Planets run out of resources. Stars, however, provide energy on a scale almost impossible to comprehend. In the 1960s, a physicist proposed a solution. Instead of living on a planet, an advanced civilization might build structures around its star to capture a significant fraction of its energy output. Not a single object, but a vast collection of components forming a loose shell. Such a structure would not need to be solid. It could be incomplete, fragmented, evolving. This concept remained theoretical, interesting but distant, something to discuss in lectures and thought experiments, not in connection with real data. Until this star. When astronomers placed the observations side by side with the theoretical expectations, certain parallels were impossible to ignore. A large fraction of starlight blocked, irregular shapes, no clean periodicity, no obvious planetary explanation. The idea was deeply uncomfortable. No one wanted the conversation to drift toward speculation. Science demands restraint, but science also demands honesty. When data refuses to fit existing frameworks, new frameworks must at least be considered. Privately, some researchers began asking the question, not because they believed it was true, but because they could not prove it was false. If a civilization were harvesting energy from a star, the structures involved would not behave like planets. They would not orbit neatly. They could shift positions. They could be built, dismantled, and rebuilt. They might cast shadows of varying depth and duration. From a distance, the light curve could look exactly like this. That realization was unsettling, not because it suggested intelligent life, but because it exposed a blind spot. Humanity had never truly considered how artificial structures might appear at interstellar distances. The theory did not require intent to communicate. It did not require signals. It did not require contact. It required only engineering on a scale far beyond human capability. That scale was the problem. If such a structure existed, it would represent a level of technological advancement almost impossible to imagine. It would imply a civilization millions of years ahead of humanity, stable, persistent, capable of manipulating matter on stellar scales. That is why the idea was handled with extreme caution. Publicly, scientists emphasized natural explanations, dust, debris, comets, but in private discussions the megastructure hypothesis lingered, not as a belief, as a placeholder for ignorance. It was a way of saying, we do not know what this is. The media, however, seized on the idea almost immediately. Headlines simplified it. Speculation turned into sensation. Alien technology became the narrative. Scientists pushed back, emphasizing uncertainty, but the conversation had already escaped the laboratory. What made the situation more tense was that the hypothesis made testable predictions. If such a structure existed, it should emit waste heat. Energy captured must eventually be released. Infrared telescopes could detect it. That meant the idea could be tested, and testing it meant confronting the possibility directly. Some researchers worried that even mentioning the idea would damage credibility. Others argued that ignoring it would be dishonest. The balance between skepticism and openness became delicate. Behind the scenes, the debate intensified. No one claimed to have found evidence of extraterrestrial intelligence. That was never the conclusion. The real issue was simpler and more disturbing. For the first time, astronomers had data that could not decisively rule out an artificial explanation. That had never happened before. Usually, alien hypotheses collapse quickly under scrutiny. This one lingered longer than expected, not because it was strong, but because everything else was weak. As telescopes prepared to observe the star in new wavelengths, the scientific community waited. Not for confirmation, but for elimination. Because if the megastructure idea survived the next test, the implications would be profound. And if it failed, the mystery would not end. It would only deepen. When the world found out, the story of the star began in the quiet halls of academia, but it did not stay there for long. As data accumulated and anomalies became impossible to ignore, the mystery crossed the boundary from scientific curiosity to global fascination. What was once a footnote in a research paper became a question whispered in newsrooms, forums, and online communities around the world. It started slowly, A press release noted the unusual behavior of the star, describing dips in brightness that were larger and more irregular than anything previously observed. The language was careful, measured, precise, as scientists always are when uncertainty is high. But the phrasing carried weight. Something unusual was happening in the sky. The media picked it up, and suddenly what had been a minor observation became front-page news in science sections everywhere. Headlines hinted at possibility without claiming certainty. Some were cautious, others sensational. Within weeks, speculation had spread across continents. Internet threads buzzed with excitement, fear, and disbelief. Citizens who had never thought about distant stars began to debate what might be out there. And the world's attention was drawn even further when citizen scientists joined the investigation. Amateur astronomers, hobbyists with telescopes and a hunger for discovery, began analyzing the publicly available Kepler data. They re-examined light curves, plotted graphs, and compared the star, dimming to that of thousands of other stars. Some made small discoveries, identifying subtle dips previously overlooked. Others, perhaps unknowingly, fueled speculation by suggesting possible artificial structures as a cause. Meanwhile, serious researchers stepped up their efforts. SETI, the search for extraterrestrial intelligence, aimed its powerful radio telescopes toward the star. Observatories around the world tracked its behavior. Universities and private research groups coordinated efforts to monitor the dips in real time. Data poured in from multiple sources, creating an unprecedented multi-layered picture of the star's activity. Every team hoped for a natural explanation, but the patterns persisted. There was no simple cause, there was no definitive answer. The scale of attention was unprecedented for a single star. Astronomers found themselves caught between rigorous scientific process and the public's insatiable curiosity. Each new observation could make headlines within hours. The story became a social phenomenon, sparking debates in classrooms, homes, and online forums. Speculation about alien megastructures gained traction not because it was proven, but because conventional explanations were failing. People were drawn to the unknown, to the idea that perhaps humanity had glimpsed something truly extraordinary. Even governments and space agencies began to take note. While official statements remained cautious, internal communications reflected concern and intrigue. No protocol existed for dealing with something this ambiguous. Was it a rare natural phenomenon, or was it evidence of intelligence far beyond human understanding? The answer remained out of reach, suspended in the cold light of the distant star. The attention had consequences beyond science. The public debate fueled interest in astronomy and space exploration, drawing new enthusiasts to science programs and educational platforms. Popular science channels saw spikes in viewership. Online communities exploded with theories, analyses, and debates. Each new dimming event reignited the conversation, creating cycles of curiosity and suspense. Yet for the scientists, the stakes were more personal. Their reputations, their research funding, their credibility rested on how they interpreted the data. They had to be cautious, but they also had to confront a phenomenon that defied expectations. Each dip was a reminder that the universe could surprise even the most experienced observers, and that surprise was not necessarily benign. It was subtle, unsettling, and profoundly challenging. In the end, the star became a shared mystery, not just a topic of scientific inquiry, but a question for the world. It reminded humanity that the universe is vast, unpredictable, and still largely unknown. And it forced us to consider possibilities that had once been confined to thought experiments and science fiction. What humanity saw in this star was not just light dimming. It was a reflection of our own curiosity, our desire to understand, and our confrontation with the unknown. And that confrontation was only beginning. The heat that never came. When speculation about the star reached its peak, a crucial test was proposed. If something enormous was blocking that much starlight, it had to obey the laws of physics. Energy does not disappear. Matter does not remain cold while absorbing immense amounts of radiation. An object capable of obscuring 20% of a star's light should emit heat, at least some detectable signature. Astronomers turned their instruments to the infrared spectrum. Infrared light reveals warmth invisible to the naked eye. Stars, planets, clouds of dust, and even human-made satellites all radiate in this spectrum. If the dimming were caused by natural material, astronomers expected a faint but measurable heat signature. If it were artificial, there might also be detectable thermal footprints. Either way, something had to appear. Nothing did. Observations using multiple infrared telescopes returned a consistent result. The star's surroundings showed no significant heat, no warming from a massive dust cloud, no radiation from debris, no trace of matter that could account for the dips. It was as if something enormous, capable of blocking light, was perfectly invisible in infrared. The universe had presented a puzzle so strange that it defied expectations. This outcome forced scientists to confront the limits of their understanding. If nature could create something this opaque and cold, it was unlike anything previously documented. If human or alien engineering could be responsible, it was beyond imagination, silent, and efficient in a way that seemed almost impossible. Either scenario was unsettling. The absence of heat also called into question the leading natural explanation, a cloud of dust or debris. Dust scatters light and absorbs it, re-emitting energy in the infrared. But despite careful measurements, the expected glow did not exist. Astronomers tried adjusting models. They considered smaller particles, unusual compositions, even exotic materials. Each modification helped explain one detail while breaking another. Nothing fit perfectly. The infrared silence persisted. This silence carried a psychological weight. In science, absence of evidence is not evidence of absence, but when something should be present and is not, the mind struggles to reconcile expectations with reality. Scientists privately acknowledged it. Publicly, they remained cautious. They used careful phrasing and hedged conclusions, yet every new observation reminded them that the star refused to conform to known rules. The effect on the public was profound. For enthusiasts and theorists alike, the lack of heat fueled imagination. Could this really be a megastructure? Could a civilization engineer something on a stellar scale so efficiently that it left no thermal trace? The idea shifted from science fiction to a question that could not be entirely dismissed. Discussion threads and media coverage exploded with theories. Some suggested material science beyond human capability. Others speculated about the very nature of the universe and what might be hiding within it. For the astronomers, the situation was both exhilarating and terrifying. Exhilarating because it challenged the limits of observation and theory. Terrifying because it reminded them how little is truly known. The star had become a mirror reflecting humanity's deepest uncertainty about the cosmos. In the scientific community, debates intensified. Some researchers doubled down on natural explanations. They explored phenomena such as unusual interstellar clouds, new types of variable stars, or completely unexpected astrophysical events. Each possibility was examined in depth, every assumption questioned. Yet with each study, the heatless nature of the phenomenon remained a barrier. The star refused to yield a complete answer. In this tension, the mystery deepened. Observers realized that the star's behavior did not just challenge specific hypotheses. It challenged the way scientists conceptualize stellar systems, energy, and structure. It demanded humility and patience, and for the rest of humanity watching from afar, it demanded imagination. The star had become more than a scientific curiosity. It had become a question without an easy answer. Something in the universe was behaving in ways that were entirely unexpected, invisible in ways that should not exist, and persistent in ways that demanded attention. It was a reminder that even in an age of satellites, telescopes, and deep space observation, the cosmos could still surprise. The heat that should have been there was not. The evidence humanity expected to find was absent. The star continued to dim, silently refusing to explain itself. And that absence made the mystery all the more compelling. Why scientists still aren't done watching it? Years have passed since the first curious dips were observed in the star's light. Many mysteries in astronomy are fleeting. A sudden flare, a transient comet, a momentary anomaly in data. Most of these events fade from memory after careful explanation. Not this star, not this one. Its behavior has persisted, and with persistence comes obsession. Astronomers continue to monitor the star with an intensity reserved for phenomena that challenge fundamental understanding. Every new observation is a puzzle piece. Each dip is logged, plotted, and scrutinized. Light curves are examined with extreme precision. Teams around the world coordinate to ensure that no event goes unnoticed. Amateur astronomers remain involved, providing independent verification. The effort is unprecedented for a single star that does not emit danger, light, or sound. Its importance lies entirely in the questions it raises. The star refuses to fit known categories. The leading dust cloud hypothesis explains some observations but fails to predict others. Irregular dips continue. Some light drops are subtle, others dramatic. Some last hours, others days. The pattern of dips does not repeat reliably. Each new observation forces researchers to reassess assumptions, re-examine models, and re-examine what they thought they knew about stellar systems. This persistence has broader implications. Scientists realize that if a star can behave like this, there may be many more examples waiting to be discovered. Patterns previously assumed to be anomalies may in fact represent a class of phenomena that are poorly understood. Monitoring this star is not just about solving a single mystery. It is about redefining the limits of observation and expectation. It is a test case for the unknown. The continued attention has also created a culture of anticipation. When a new dip occurs, telescopes are directed, measurements are taken, and simulations are updated. The global scientific community is united in watching the star. This coordination has created an unusual situation in astronomy. Typically, stars are observed as part of routine surveys. They are catalogued, monitored periodically, and then left alone. Not this one. It commands resources continuously. It demands vigilance. It reminds humanity that the universe is still capable of producing surprises. At the same time, the persistent mystery invites imagination. Every dip becomes a story in itself. What if the explanation is not natural? What if there is intelligence behind the patterns? Scientists emphasize that this is speculative, yet the very fact that natural explanations struggle gives room for thought. Even the most cautious researchers admit that the star forces them to consider extremes, at least mentally. It is a rare phenomenon where data intersects with the limits of imagination. The long-term observation has also created a historical record. Decades of light curves now exist. Patterns within patterns may be discovered as techniques improve. Machine learning and advanced analytics are applied to search for subtle correlations previously invisible. Every year, the star provides an opportunity to test methods, refine instruments, and challenge conventional wisdom. It has become a laboratory not only for understanding itself, but for expanding the tools of astronomy. Most importantly, the ongoing mystery keeps viewers engaged. The public, fascinated by irregularity, complexity, and uncertainty, continues to follow developments. Scientists share updates in journals and popular media. Each report rekindles interest. Each anomaly triggers discussion. The story has become part of a collective experience, blending education, speculation, and wonder. Humanity watches not because the star threatens life, but because it challenges understanding. It reminds us that the universe is not fully comprehensible and that discovery is never complete. The star is still out there. It continues to dim, to fluctuate, and to confound expectations. Observers know they may never have a final answer, but the act of watching, measuring, and questioning is its own reward. It is a reminder that science is as much about curiosity as it is about certainty. And for as long as the star refuses explanation, humanity will remain vigilant, patient, and endlessly fascinated. The mystery is alive. It refuses to fade. It refuses to conform. And that is exactly why scientists are still watching it. After years of observation, countless studies, and heated debates, the star remains a mystery. It shines with a quiet persistence, dimming unexpectedly, fluctuating unpredictably, and refusing to conform to any known pattern. For astronomers, the phenomenon is not a story with a neat conclusion. It is a reminder that the universe is vast, indifferent, and far more complex than humanity often assumes. The star teaches a lesson that is both humbling and unsettling. Science thrives on explanation. Observation leads to hypothesis. Hypothesis leads to theory. Theory leads to understanding. Yet here is a star that defies every step of that process. Observers can measure its brightness, record its dips, and model its behavior. They can propose explanations, test predictions, and reject impossibilities. But no matter how many methods they employ, the star continues to resist final understanding. That resistance is not failure, it is revelation. It reveals the limits of knowledge. It forces observers to confront the fact that there are phenomena beyond current comprehension. It reminds scientists and enthusiasts alike that certainty is provisional and that curiosity is infinite. What makes the mystery even more compelling is the scale of the unknown. The star's dimming is not minor. It is vast. It involves light, energy, and matter on scales that are almost impossible to visualize. A star losing up to 20% of its brightness is an event that should have immediate, observable consequences, yet those consequences remain elusive. Infrared observations reveal no heat, spectral analysis shows no anomalies, and gravitational calculations fail to indicate massive companions. The star continues to exist in a state that is simultaneously extreme and quiet. This paradox has captivated the public imagination. Some speculate about alien megastructures, others search for undiscovered physical processes. Conspiracies flourish, theories are debated, and yet the truth remains hidden. For the public, the allure is not the answer itself, but the gap between expectation and observation. Humans are naturally drawn to mystery. They are compelled by phenomena that challenge the familiar. This star delivers precisely that, day after day, observation after observation. For scientists, the fascination is deeper. Each new dip is a puzzle. Each variation in light curve is a test of understanding. The ongoing study pushes the boundaries of astrophysics, instrumentation, and methodology. Teams develop new models, refine their simulations, and deploy ever more sensitive equipment. What makes the star extraordinary is not merely its behavior, but the way it reshapes thinking about what is possible in stellar systems. Despite decades of monitoring, the ultimate cause remains unknown. It could be natural, it could be artificial, it could be a combination of factors as yet unimagined. The uncertainty does not diminish the significance of the observation. Instead, it enhances it. It transforms the star into a symbol of the unknown. It reminds humanity that the universe is still capable of surprising even the most knowledgeable observers. The quietly unsettling truth is that the star may never reveal its secrets fully. Some questions may remain unanswered indefinitely. The more scientists learn, the more questions arise. It is a phenomenon without closure, without finality, and without reassurance. And that is precisely why it captivates. The mystery does not end, it persists. It invites curiosity, it challenges understanding, it humbles anyone who dares to study it. In the end, the star does not provide proof of life beyond Earth. It does not confirm artificial structures or unknown physics, yet it achieves something equally profound. It forces reflection, contemplation, and wonder. It reminds humanity that the cosmos is larger, stranger, and more unpredictable than imagined. It shows that even in an age of technology and knowledge, the universe can surprise in ways that inspire awe, fascination, and a little quiet fear. The star continues to shine, quietly defiant, dimming without explanation, and reminding everyone watching that the universe is full of questions we have yet to answer. It does not shout, it does not signal, it exists. And that existence is enough to captivate, challenge, and inspire for generations to come. This star continues to dim, quietly defying explanation, reminding us that the universe is far stranger than we can imagine. What do you think is causing it? Could it be something natural, or is there something intelligent at play? Comment your theory below and subscribe to explore more mysteries of the universe. Hit the notification bell because the story of this star is far from over. If you want more videos like this, hit the like button, share, and comment. Your engagement helps us bring even more astonishing mysteries to your screen.